Back to BME 2315. Today we'll be talking about the next section of our course called optimization. So as we discussed last time, there are several methods available for optimization. The bracketing method that we talked about was called the golden section search, and the basic idea is that you had a lower guess and an upper guess, and if you had the lower and upper guess, it could gradually but slowly converge on a single maximum of that function. It was guaranteed to find it if it exists. However, one of the disadvantages of that method is that it can be slow. And so today we're going to be talking about two alternative methods called the steepest ascent method and Newton's method. And both of those just require you to have one initial guess. That's why they're called open methods. And they have somewhat different properties that have advantages and disadvantages that we'll discuss. So the simplest of these is called the steepest ascent method. And basically what it's saying is that it takes an initial guess, a single initial guess, at where the optimum is, and then it adds that to a step size h multiplied by the first derivative. So that's really like a disadvantage compared to the golden section search only needed function values, but the steepest ascent method requires you to compute the derivative. Okay. And so what this looks like, this method looks like that you have a single parameter h that you'll have to specify. And it's not always clear what the best h would be, but we'll discuss the implications of that in just a second. The basics of the method is if you say had a function f of x was 1 minus x to the 4, then it might look something like this. And I'm going to also plot the derivative would be a little bit flatter than that. Yeah, something like that. Okay, so what will happen is if you start at some location x0, then the derivative is high right here. And so it'll take a big jump. So it'll take a big jump and say then it lands at this location x0 at x1. But at x1, the derivative is much smaller, so it'll take a smaller jump. And then it's even shallower at the x2 location. So it takes smaller and smaller jumps. So basically, that's why if h is too small, it'll converge slowly. And especially, not actually, let me rephrase. As you approach the optimum, the steepest ascent method will go more and more slowly for most shaped functions. And in terms of the step size, you have to watch it because If it's too small, then that'll also make it converge slowly. And the other negative of this method is if it's too big, you may actually jump over the maximum of your function altogether. So let's take a look at how we can apply the steepest descent method, which is really the simplest of the optimization methods. Okay, so as we did with the golden section search, we're going to use the same function so that you can see the same function from multiple angles. And we need to first start off by specifying an initial value where we're saying that we're starting at x equals 0.5. Okay, and then we're going to say that using the formula on the top right, that x1 equals xi, so x1 equals x0 plus h f prime at x0 equals 0.5 plus 0.2, because this is our step size. And then if we evaluate the function, there we get 0.831. So remember that 0.831 is not the y value, it's the x value, it's the x location of where we think that the maximum is occurring. And so if we plug in this value for x1 into our function, we get 5.408, which is not a bad estimate given that this is our very first try. So let's just try that again now to do one more iteration. So we got x2 is x1 plus h times the derivative at x1. Remember, the x1 is at 0.831. And so then that equals 0.831 plus 0.2, which is our fixed step size, times 1.182. So there's a dot there. And so this is our x location now, guessing for where the maximum is. And if we plug that into our function, we get that f of x2 is 5.638. So this is basically you repeat this process as many times as you like, up to whatever stopping criteria you set up. So one of the problems we've said is that this method can converge slowly. So we wanted to see an alternative to the steepest descent method that might go more quickly, and that's called the Newton's method. Newton's method is the basic idea is that rather than just using the f prime, we are going to take the ratio of that with a f double prime. And a few properties or things to know about. So the Newton's method sometimes gets confused with the Newton-Raphson method for root finding. And so sometimes we'll say, for optimization. But basically, when it's just Newton by itself, then that means it is the optimization version. Okay, so one of the properties of this is that it will not just find maxima, it will find both maxima and minima. In other words, it finds locations where the f prime is 0. Okay, and so let's take a look at how that works. So say we had our previous function that looked like something like this. Then f prime was going to look like this. And then f double prime is going to be negative 12x squared. So basically, in the regions where f prime was small, that was making small step sizes, f double prime is also going to be pretty small. And so that kind of cancels each other out in a sense, to make it more likely that you'll take bigger step sizes. I apologize, my pen is acting slowly again today. So it has an advantage of being faster, but it requires f double prime. So there's more information that you need to be able to provide it, and it may diverge. So there's just certain function shapes that it will not find the maxima or minimum for. Okay, so that's what the Newton's method looks like in abstract, where it looks a lot like steepest descent, but instead of the step size, we're replacing in the denominator with f double prime. So let's look at how you would apply that in an example. So we're going to use the same formula that we've had before so that we can compare the performance. And we say that x0 is 0.5, and we'll do a couple kind of simple calculations that help us along the way. We know that we're going to have to take the f prime, and we're going to add it, and that will be that. And we'll also have to take the f double prime, 0.5 equals negative 1.159. Okay, and so now let's start using Newton's method. So x1 equals x0 minus f prime of x0 over f double prime of x0. Okay, and then if we throw in these values, we get 0.5 minus 1.1655 divided by negative 1.59. And so that gives us that x1 is equal to 1.928. Now, if we plug that into our function to see how high that is, we get 5.502. Okay, and if we compare that back a couple of slides, that's better than before. So before, after one iteration, we were at 5.4, and here we're at 5.5. Okay, so now we'll apply this to the second iteration. So we'll say that x2 equals x1 of f prime of x1 over f double prime of x1. That equals 1.928 minus 1.086 divided by 2.074. You have to plug those in. Sorry, those didn't show up before. You'd have to plug those into these formulas in order to get these values. And you get 1.405. And if we check how high that is, f of x2 equals 5.775. So that's the height of our function, and we see that it did much better than golden section or steepest descent. Basically, this is a really nice method most of the time, but you need to, but its disadvantages are that you need to know how to calculate the second derivative very easily, and it also has the potential to diverge. So to summarize these methods that we've talked about, talked about the golden section, where golden section only calculates maxima, whereas Newton's method calculates maxes or mins. The golden section rule must bracket the optimum, so you need to know lower and upper bounds that surround that maximum. But the advantage there is that it will find it. It's guaranteed to find a maximum if it's there. Whereas, in contrast, Newton's method can diverge. And finally, golden section method does not require any derivatives, whereas Newton's method, you must be able to take both the first and second derivative. And the steepest ascent method is kind of in between, where it finds maximas. It only needs one starting point, but it must be able to take the first derivative, and it converges fairly slowly. So what you see here is that each of these methods have various different advantages and disadvantages. I'd say that Newton's method is nice because it converges very fast, but you also need to take care that the solution is actually converging to something that looks stable. And finally, the steepest ascent method has this required parameter h, and it's not always clear what value you should use for that, and so you may need to try a few things that could affect the convergence rate quite a bit. So thanks. Just to give you a preview of where we're going next, so far we've looked at optimization in one dimension. Next, we're going to be looking at optimization in two dimensions or more. So hope to see you soon. Hope that is helpful to you. Bye.